For our last topic in static fluids, I want to talk about the buoyant force, or buoyancy. So the idea here is that if we have an object that is touching a fluid, that object feels a force from the fluid, and it feels a net upward force from the fluid. So this is a upward force from the fluid on an object. And so the size of this force, this buoyant force, FB, is equal to the following. It is equal to rho g v displaced. Okay, so this is our equation for buoyant force. G here, we know G is 9.8. Rho here is the density of the fluid, and this is important. The buoyant force does not depend on what the object is made of. It only depends on what the fluid is. And V displaced is the volume of fluid that is displaced by the object, meaning the object is keeping it from being where it wants to be. So, a little bit more about V displaced. So if we have an object that is like all the way immersed in liquid here, V displaced is just equal to the volume of the object, right? The object is, if the object wasn't there, this space would be filled with water, and it would be filled with exactly as much water as the size of the object, right? So the volume of fluid that's displaced is the same as the volume of the object. That is not the case if we have an object that is only partly immersed in the fluid. So here, for this object, it still feels a buoyant force because it still is touching the fluid, but this V displaced is only equal to the volume of the object that is under water. Or I'll say that is below the surface. So the volume that I've shaded there is the volume displaced that we would use. So so this equation does not depend on the depth in the fluid by itself, although in some fluids, like we said, the density of the fluid may change as we increase our depth in the fluid, and also, as this object moves up and down, more or less of it is underwater, and so therefore the volume of fluid that it's displacing would also depend on that. All right. I'll emphasize again, this does not depend on the density of the object. This is just the density of the fluid. That's a common mistake. Okay, so if we have an object that is in this fluid, we can use the equation. So the fluid has some density and the object has some density. You can show that, and we will show, that the net force on this object is going to be downward if its density is bigger than the fluid density. And the net force is up if it's the other way, if the object density is less than the fluid density. So this is what's normally referred to as buoyancy. So if an object is positively buoyant, it will have an upward force because its density is low. It will be negatively buoyant if it has a downward force because its density is higher. And it will be neutrally buoyant, a net force of 0, if the two densities are equal to each other. So for scuba divers or other divers, getting neutrally buoyant is often a goal so that you are not feeling this net force from the water on you. If you can adjust your density to be exactly the same as the density of the water, the net force on you from those is going to be 0, and you're not going to change your depth. I should say this is the net force of the buoyant force and gravity combined. So this is, maybe I'll give a problem where we show this. Okay, so this is some practical knowledge about buoyancy. One other thing I wanted to say, when we have an object floating on the surface of a liquid, I said liquid. This could be a fluid, it doesn't have to be a liquid necessarily. So if we have an object that's on the surface, that is, it is partly above and partly below, the volume so this is our object, this is our fluid, the volume that's displaced is less than the volume of the object, right? But if this object is sitting here floating, like if it is sitting there floating, not moving, we know that the forces on it are 0. So if we're in equilibrium, the net force is equal to 0, which means our buoyant force is equal to the force of gravity. So what has happened there is our force of gravity, let's just plug in for these. Our force of gravity is equal to mg for the whole object, right? The mass of the whole object. The buoyant force is equal to rho g times v displaced, the amount of fluid that's being displaced. And this rho is the density of the fluid, FL. I could plug in for this mass as the density of the object times the volume of the object, right? The mass of the object is its density times its volume. Okay, so the reason I'm doing this, oops, I have a G here too. So I have rho of the fluid times G times V displaced. My G's cancel. And if I want to solve for how much of this is below the water, so this V displaced, I can solve this equation for that. So the volume of my object that is displaced is equal to the volume of the object times rho object over rho fluid, the density of the object over the density of the fluid. So in other words, if I have, like right here, I have 2/3 of this object below the surface, let's say. So V displaced is 2/3 of V object. That means that this fraction is 2/3. In other words, the density of my object is 2/3 of the density of my fluid. So that's kind of a cool rule of thumb. By just looking at a picture of an object floating on the surface, if you can estimate how much is above and below the surface, you can estimate what the density of that object is relative to the density of the fluid it's on.